Worked problems for Chapter 19. This is for Chem 1412. This is taken from several sources. Let's go to the next slide. So most of these problems are going to be coming from the Zumdahl text. That's the chemistry text. A few of them are taken from Brown and LeMay, and maybe occasionally there will be one from McMurray. So just to give credit for those. So the problems, just to be clear, are taken from those texts, but the answers are provided by the author. Next slide. So the solutions here, as I just said, are provided by me. Next slide. All right, so I'm going to try to use the laser pointer here, or the marker, and we'll see how this goes. All right, so these problems are very straightforward. And so I think the one formula that you're going to need to remember more than anything else is going to be delta G equals delta H minus T delta S, where the T is the absolute temperature. So one of the things you'll always want to remember is to change it if it's given in centigrade. And then another little clue, if you'll look here at problem 1, the 31 there, that indicates this is from Zumdahl. Excuse me, the top row. For ammonia, the enthalpy of fusion is 5.65 kilojoules. So if I were you, you want the units to match with entropy, which are given in joules. And it's almost always going to be this way, so I would go ahead and convert the kilojoules to joules. And that way you've got matching units. And the reason that the entropy is given in joules per K is because you're going to multiply that every time by T. When you multiply by T, the K goes away because those units cancel. So, all right, so let's just look at part 1. Here, number 1, the enthalpy is given and the entropy are given. So delta G is delta H minus T delta S. So what that means is that we have all the information we need to find what the delta G is. Now, the part A there doesn't specifically ask us to find that, but by finding that, we can answer the question. So what we'll do is for part A, we'll just find delta G, and then what we want to do is look to see if it's negative or positive. If it's negative, that means it will spontaneously melt. So there's your key word there, spontaneously. If it's negative, if your delta G is negative, as we mentioned in the lecture slides, that means that it will proceed spontaneously. So we're assuming a direction of solid to liquid here. All right, so just find delta G and see if it's negative or positive. And then for part B, what is the approximate melting point of ammonia? The way you would do that would be to use, again, the same formula. So you'd be using delta G equals delta H minus T delta S, where you'll leave the T as a variable, or if you want, you can replace the T with an X if that makes it easier. And then for delta G, remember that when you're at the melting point, as we said in the lecture notes, that means that you're at an equilibrium point. So what will delta G be if you're at an equilibrium point? And it will be 0. So just set 0 equals delta H, which is given, minus T, which you'll leave as a variable, times delta S, which is given. So let's go to the next slide. Okay, so we'll use this formula for part A. So if you'll look at A, come down to delta G equals 5650 joules per mole. That's given in the problem statement, minus 200 K times 28.9 joules per mole K. So all of that was given in the problem statement, including the temperature. And then just go ahead and do your math, and you come up with an answer of minus 130 joules per mole here. Let me just kind of underline this. So that means because of this negative sign here, that means that this process will be spontaneous. Okay, so that's all you have to do. Just see if it's negative or positive. And then to find part B's approximate melting point, you just want to set delta G to 0. Again, the reason is because if you're at an equilibrium point, then delta G will be 0. And the melting point of anything is an equilibrium point. And the reason is because you've got, for example, in the melting point, you've got things going from solid to liquid, and in the other direction. So set that delta G is 0 equals 5650 minus T or X, whichever you prefer, times 28.9, and solve for X. And very, very simple. When you do that, you get 196K. Now we're going to find that a lot of the problems here, especially early on, are going to be just like this, using the same formula. And I'm going to go to the next slide. All right, consider the reaction here. This one is going to be something you'll likely see on the tests. We've got 2O going to O2. So how many entities do we have on the left? Well, we have O's there, just O atoms. But we have 2 of them, whereas on the right, we have an O2. So we have the same number of O's, but they're combined differently. So on the right, that's only one entity. So we're going from 2 to 1, so that means that the delta S is negative, because it's getting smaller. But that's not the way that we would want it to be if we were trying to get this to be spontaneous. So remember, there are 2 things that can make it spontaneous, and that is if the delta S is positive, but it's not here, or if the delta H is negative. So if you look at that, the way it's written, it's only written going to the right, which is an indication that this is spontaneous. It's like a clue. And it isn't the delta S that's making it go to the right. So what does it have to be? It has to be the delta H, which means the delta H has to be negative, because a negative delta H indicates a reaction that will be spontaneous and that will be exothermic. So would the reaction in part B be more spontaneous at high or low temps? Well, the entropy term is the one that's multiplied by the absolute temperature. It's delta H minus T delta S. So the term that is influenced by the temperature is the delta S term. So if the delta S is unfavorable towards spontaneity, then you would want the temperature to be low. You want that term, T delta S, to be less important, and it would be less important if the temperature were low. Next slide. Okay, so here are your answers, which since I don't have to rush quite as much this time, I'll just let you look at these for just a few seconds, or you can pause. Okay, so next slide. Actually, let's wait just a few more seconds. All right, next slide. Okay, so for the reaction at 298K, 2NO2, double-headed arrow N2O4, the values are given for delta H. These are delta H standard and delta S standard. That just means you're doing it at one temperature of 298 in 1 atmosphere. And then the second part, let's just wait and we'll come back to that. So for the first part, what is the value of delta G at 298K? Well, we're at 298K, as we can see here, the degree sign indicates we're at 298K, unless they tell you differently. So delta G, just use the same formula, delta G equals delta H minus T delta S, where the T will be 298. Delta S is going to be minus 176.6. Again, I'm just reading from up here. And then the delta H is minus 58.03 kilojoules. So don't forget this one right here on the one that I'm marking right now. If you can see that, you want to multiply that by 1,000. Just move the decimal place over 3 places to the right. So that's 58,030 joules per mole. And then use your formula delta H minus T delta S. And that will give you the delta G. That's all you have to do for the first part. Go to the part where it says assuming that delta H and delta S do not depend on temp, which they would. And if you take a more advanced class, like if you take physical chemistry, your 3rd year or whatever, take physical chemistry, you'll use maybe the Atkins textbook, or if you end up in grad school in this. That's the kind of thing that you would typically do, that you would do it there in a more advanced class, but you don't do it in general chemistry. So that's one of the differences. You get into it in more depth, because they really do depend on temp, but let's just go along with what they're saying. If they don't depend on temp, at what temp is delta G equals 0? So we do this the same way we did in the previous problem. We set delta G to 0. That equals delta H minus T delta S. But in that case, the difference would be that you leave T as a variable. So that's the only thing you would change. So leave T as a variable and solve for T. And then to answer that last question, is delta G standard negative above or below? Just look to see what it was at 298, and then you'll find where it's 0, and then just compare them and look back and see, was 298 above or below that, because we already know what the value, or we'll know what that value is. Let's go to the next slide. So read down to answer. Delta G standard equals delta H standard minus T delta S standard equals minus 58,030 joules minus 298 times minus 176.6. And when you do the math there, you should get minus 5403 joules, and that's at 298. Okay, all right, the next part is done below that, where you see the 0 equals minus 58,030 equals X, or you can leave it as capital T, times minus 176.6, and solve for X, and that's actually your temperature. That's the temperature at which delta G is going to be 0, and that is going to be 328. So if you look back up above, when we found the minus 5403, that was at 298. So delta G was negative below 328, so we can answer that question without even having to do any further calculations. Okay, let's go to the next slide. Consider the following reaction. We've got 2NO2 in equilibrium with N2O4. Both are gases, and we're given the delta H and delta S standard values, and we're supposed to find the value of K. So this problem incorporates one more step than what we've done up to this point. So we're going to do the delta G equals delta H minus T delta S again, but then we have to do something else at the end. So to do the delta G equals delta H minus T delta S, first of all, what is capital T? Well, it's 25 degrees centigrade, but we need to convert that to K, so add 273. That's 298 K. And then up at the delta H there, it's minus 58.03. Change that to minus 58,030. So this problem is like one we've done before. And then we'll go ahead and find the delta G, as we did before, by using delta H minus T delta S. But once we find delta G, we don't want to stop there. So again, just a warning on your final exam, be careful that you answer the question that's asked. They don't want delta G here, they want K. So, and this is all standard, so when you find delta G, you're going to be finding delta G standard. So use the second formula for the second part here, would be delta G standard equals minus RT logarithm K. And that K is KP, as we mentioned before in the lecture notes. And the R value that you want to use here is the 8.314, which you'll want to remember that. I mean, that's almost like one of the harder parts of this, is to remember which R to use for which problems, or usually in each chapter, though not necessarily, but a lot of the time, every chapter that we go to will have its own version of R. In this chapter, it's basically going to be 8.314 most of the time. And then the second part, we're going to do it again. So we have to do the whole thing over again, except that we're going to do it at different temperatures. So let's go ahead and move to the answers. So answer at the top, delta G standard equals delta H standard and so forth, minus T delta S standard. So I just substituted in the value that was given in the problem statement here for the delta H, and then I substituted in the value that was given for the delta S and multiplied it by 298. Subtract that from the minus 58,000, and I get the delta G standard is minus 5,403 joules per mole. But don't stop there. They are asking for the value of K, so use delta G standard equals minus RT logarithm K. And so K will be something we'll have to figure out after we figure out logarithm K here. So the first thing we want to do is figure out what is logarithm K. And so to do that, just divide the minus 5403 by minus 8.314 and by 298. and you get that the logarithm of k is 2.18. Now remember, to solve that kind of a problem where you have a logarithm in there, you raise both sides of the equation to e to the power of. On the left, it's e to the logarithm of k becomes k, and on the right, it's e to the 2.18, which is 8.85. Do that on your calculator. And then part B, I don't think I'm going to go through it, but you would just do it exactly the same way we just did part A. So these are identical. The only thing that's different is the temperature. When you do part B, and you might just try doing it without looking at the answer first, when you do part B, you should get K is 0.0798. Okay, next slide. Remember that you can always email with questions, or you can call. And if you lost my phone number, or you don't want to look it up, which I don't blame you because everybody's kind of busy right now, but just email me and ask for the phone number, and I'll give it to you if you're in my class. So this one is similar to the ones that we just did with a slight variation. So we need to find delta G standard for the reaction that's written across the top, not the ones that are listed below. There's two listed below. We're not interested in delta G for those two, but we'll have to use those to build the third one, which is the one at the top, which is the one we want. So we have to add somehow the ones below together to get the one at the top first, and then we'll know what the K values are for those, and then we can work backwards from the K value to get delta G standard, right? Which we'll see when I flip to the answer. So let's look at these two equations below. H2 plus O2 is H2O2, 2H2 plus O2 is 2H2O. So if we add them the way they are right now, we would get something that we don't want at all. So the easiest way usually to solve these is to look at the one you do want and see if the things below are on the correct side. So first of all, we can see right off the bat that the H2O is on the wrong side in that second one below. It's listed as 2H2O, and here it's listed as 2H2O, but we don't want it on this side. We want it over here on this side. So how can we get it over there? Well, we can just flip the direction of that bottom reaction. So it's really, really hard to draw with this, but just flip it. So in other words, you're going to make it so that it says 2H2O gas, double-headed arrow, 2H2 plus O2. Then when we do that over here at the right with a K, we have to take the reciprocal of that. In other words, the new K for that, if we flip it, would be 1 divided by 1.8 times 10 to the 37th, which is going to be something like something on the order of 10 to the minus 36th. But that still won't quite get us there because we've got 2 here, right here. We've got a 2 in front of the H2O. And up here in the one that we're trying to get to, we've only got a 1. So, but that's easy to fix, right? Can you think about how we could fix that? We just multiply that 2 right there by 1/2. But if we do that, we also have to multiply this by 1/2. And we also have to multiply this by 1/2. And we also have to, do we have to then take 1/2 times this? And the answer is no. So we do multiply everything in the reaction by 1/2. But for the K, remember the rule is that if you multiply everything in the reaction by 1/2, to change the K to its new value, you take the old K raised to the 1/2 power. Or in other words, you just take the square root of it. So the bottom line is that for that K, you're going to first of all have to, it doesn't matter the order, but at some point you'll have to take the square root, and then at another point you'll have to take the reciprocal. And when you do that, then you'll have the K for the way it should be. So at this point, let's flip to the next slide. All right, so up here at the top, these steps here, I'm just walking you through what you would have to do to get everything the way it needs to be. And then if you look over here at part 4, once we've done that here, we should be getting what we wanted. And so just compare this right here with what's written up here at the very top here, and it's the same thing. So what we would do then, and I've taken you through the steps of how to find the new K. So the last one that we wind up with here for the K for this reaction over here, there, is K2 equals 2.36 times 10 to the minus 19th. All right, so if we're adding these two equilibria together to get a third equilibrium, like the one at the top, then the way that we do that as far as the constants are concerned is to multiply the top constant, the 2.31, times the bottom one, which is the 2.36 times 10 to the minus 19th. So it would be 2.3 times 10 to the 6th here, times 2.3 times 10 to the minus 19th here. So just multiply those together, and that's done right here. And you get 5.43 times 10 to the minus 13th. Okay, now, but we're still not finished, right? So what we do next is we need to use the delta G equals minus RT logarithm K to get delta G standard. So we have K, so just take the logarithm of that. So in your calculator, just whichever way you do logarithms, on mine, I think first type in the number. So you type in 5.43 times 10 to the minus 13th and then hit logarithm of answer, and you'll get minus 28.24. And then if you come down here to this equation, you would then multiply that minus 28.24 times R and then times T, again, where the R is 8.314, and then there's a negative in there, and that's part of the formula. So minus 8.314, and I'm just giving the numbers, times 600, which was given in the problem statement, 600 kelvins, times minus 28.24, and that will give you your answer. So you're finally finished. All right, next slide. Okay, so here I put a couple of problems here that I took out of Zumdahl. In case you hadn't already known this, the difference in the chapter numbers is because a lot of the slides that I took from the lecture notes were taken from Zumdahl, and he's off from Brown and LeMay by a couple of chapters. For these two problems, I'd like for you to try them on your own. And remember, when you find that K, like for example here, when you find K, which it shouldn't be too difficult for you to do that, remember that that's KP. Again, you'll need to know that for for problem number 77. So that K is K sub P. So that should help you to be able to do that problem. So go ahead and try these two. There's two here. The first one deals with ATP. The second one deals with just a reaction. And so try those, and you should be able to do them. But if you can't, just email me and I'll help you with them. Next slide. All right, so let's kind of take a little bit of a mental break here and do some easy ones. What can be said about a chemical system that has reached a minimum in free energy? And I'll let you look at that for just a few seconds. I'm going to spend a little more time on this one, but that's mainly because we don't have as much to go through. But when we get back into the lecture notes, like for chapter 20, I'll have to kind of speed it up a little bit because the problem is that if I go over about an hour and 15 minutes, it takes literally forever. Well, not literally, but it takes a very long time to convert them into a video and then to upload the video into YouTube. I mean, we're talking like over 2 hours to do the whole process. So I still need to keep these file sizes as low as possible, although I'm not as concerned about this one because there's just not that much here. So, all right, anyway, so look at these answer choices for just a few seconds. And which one would you pick? And hopefully you picked C. So what can be said about a chemical system that has reached a minimum in free energy? And that answer is the system has achieved equilibrium. So these other answer choices are basically just distractors. Next slide. Next slide. Okay, the value of delta G standard, and I'm reading at the bottom, 25 degrees centigrade for the formation of POCl3 from its constituent elements. And here's the formation reaction. P2 plus O2 plus 3Cl2 gives 2POCl3. All right, so remember the rule for these. It's products minus reactants, and it's actually the summation of the products minus the summation of the reactants. So for every one of the values that we use, we'll multiply by the coefficient in front. And we also want to make sure, because we've got 3 columns here across the top, so we want to choose the correct column. And so which column do we need? Well, we need the column that has the delta G values. So we want to use this one right here. Excuse me, not the other two. All right, so starting with the products, we've got POCl3 gas, which is right here. And so what we'll do is we'll start off by multiplying that times 2 because of the 2 coefficient in front of it. So 2 times minus 502.5. And then we subtract minus whatever the value is for delta G for P2. And that's a gas also. So that's going to be this one right here. So 2 times 103.7. And then minus the O2 value, but the O2 value here is 0 because there's that's a pure element and it's in its regular state at room temperature. It's a gas. And then minus 3 times Cl2 down here. So Cl2 is also 0 because at room temperature Cl2 exists as a gas. So there's no energy formation that goes into that. It's already that way. So the question might arise, why isn't P2 0 also? Because it's at room temperature and it's a pure element. And the answer is because phosphorus does not exist as a gas at room temperature. So to form P2 as a gas, you would have to sublimate it, which would require a certain amount of energy. And it turns out that it requires this much energy right here. All right, so it boils down to basically 2 times this right here minus this right here, which it's going to be about minus 1,000 minus 100, so it's going to be about minus 1109 here. Next slide. Okay, so and then this part down here at the bottom is just explaining what I just said. All right, let's go to the next slide. Look at this one. The equilibrium position corresponds to which letter on the graph of G versus F, where F is what they're using to indicate the progress of the reaction. So which letter, A, B, C, D, or E, would be the one that would be at equilibrium? So look at that for just a minute. Okay, hopefully you chose answer choice C here. And the reason is because you're at equilibrium when you're at a minimum of free energy, G. So G is free energy, and C is where you're at a minimum here. So that's the correct answer choice. Next slide. So the answer is C. Next slide. All right, another interesting problem. For the reaction C2H6 gas gives C2H4 gas plus H2 gas. We have the delta H value given here is plus 137 kilojoules per mole, and the delta S is plus. And in this case, really, to tell you the truth, all we care about is the signs. So let's think back over what the rules are for things to be spontaneous. Things tend to be spontaneous if delta H is negative and delta S is positive. So for this particular reaction, delta S is positive. So it would tend to make this reaction go to the right. However, the delta H is not negative, it's positive. So it's going in the wrong direction as far as if we want this thing to be spontaneous. So remember the formula is delta H minus T delta S, where delta G is the thing that will actually predict spontaneity. So if delta G is negative, then it will be spontaneous. So we have two terms. We have delta H and we have T delta S. The only one of those terms that depends on T is the T delta S term. In this case, we want that term the T delta S term to be more important than the delta H term. And so because it's multiplied by T, we can make it more important by having T high. Whereas if T is low, it will be less important. So what we want is a high temperature here if we want this to be spontaneous. So the answer choice here is going to be C. It's going to be spontaneous only at high temperatures. Next slide. Okay, next slide. So again, let's just go through this one quickly because we just mentioned the answer. For a reaction to be spontaneous under standard conditions, the signs of delta H and delta S must be what and what respectively. We just said this. Delta H should be negative and delta S should be positive. Next slide. And then, so the answer choice is C. Next slide. Okay, this problem number 11 is a long, hard one that you have to do a lot of calculations. It says, given this data, calculate the equilibrium constant for this reaction. To find the equilibrium constant, we first have to find what? And of course the answer is delta G. But if you look here, there's no column for delta G, whereas in some of the tables we've seen there was. They left it out here intentionally. So we have to supply that whole column first before we can do the rest of the problem. So what we would want to do would be to take the delta G for this, multiply it by 2, and then subtract the delta G for this and the delta G for this. And then whatever we get after we do all of that, then use that delta G, and delta G equals minus RT logarithm K, because that's what we're actually eventually trying to find here. So this is a really long problem because you have to use that formula delta G equals delta H minus T delta S for all three of these things on the left here. This one and this one and this one. And so, I mean, I'm not going to go through every step in the calculation, but you just do it all three for all three of those, and then come back up here and do your overall delta G for the whole reaction. And then use delta G equals minus RT logarithm K. Let's go to the next slide. So when you do the SO2 here at the top, this one, you should get minus 371,000 approximately joules per mole. When you do the O2, you should get approximately minus 61,000. And for SO3, you should get minus 471,000 approximately. Okay, and then to do the overall delta G for the whole reaction, you would just take products times the coefficient. So it's the summation of the products minus the summation of the reactants. And that's denoted here in this line here. So 2 times minus 471, which is this right here, minus 2 times 371, which is this item right here, and then minus 61,000, which is this item right here. Okay, so we're just doing this like we did before, and when we do that, we should get minus 139,000 approximately here, joules per mole. But again, don't stop here because you won't get it right. So you need to now use the next formula, which is delta G standard equals minus RT logarithm K. And now we know what delta G standard is, and it was a heck of a lot of work, right? And then we know what R is, and we know what T is, because these are the degree sign above these means they're standard values, which means unless they tell you otherwise that you're at 298 K. And so the only thing that we don't know is logarithm K. So again, just use that equation and solve it for logarithm K. So take the minus 139,000 for delta G and divide by minus 8.314 times 298. And then that will give you that logarithm K is 56.13. So you might want to pause it and try that and see if you get the right answer. And then raise both sides of this equation here to e to the power of, and that becomes K equals e to the 56th. And if you do e to the 56th, you get this right here. And that's your answer. Next slide. The equilibrium constant for the following reaction is 5E8 at 25 degrees centigrade, or 298 Kelvin. The value of delta G will be blank. So what we're concerned about in this problem is this number right here, because this is K. So remember the formula is delta G standard equals minus RT logarithm K. So you know what K is, so just go ahead and take the logarithm of it and then multiply it by the temperature, which is 298 here, and then multiply by minus 8.314. Next slide. So it's done for you here. Here's the formula, and then here are the numbers put into the formula for you. When you take the logarithm of 5 times 10 to the 8th, you get 20.03. So multiply that times 298 and 8.314 and minus 1, and you get minus 49,626. And then that would round to 2 sig figs, would round to minus 50 kilojoules per mole. Next slide. The thermodynamic quantity that expresses the degree of disorder in a system is called, and so look at that for just a few seconds. Which one of these would it be? It would be the entropy, right? So this one's very easy. Next slide is the answer. Next slide. Delta S will be positive for which reaction? Okay, in other words, if it's going to be positive, it means we're going from one thing on the left to two on the right, or from two things on the left to three things or four things on the right. In other words, we want to find the one of these 5 choices where the number of entities on the right is greater than the than the number of entities on the left. So here, let's just do these one at a time. So here at the top, we're going from 3 to 2. So that's going in the wrong direction. That's going to be a negative delta S. Here we're going from 2 to 1. That's negative. Here we're going from 1 to 3, right? So we've got 1 here and we've got 2 here. So this is going to be our answer. This is going from a smaller number to a larger number. So that's it. Here we're going from 3 to 2. And here we're going from 1 to 1, so that one doesn't change. So what would the delta S be for that one? It would just be 0. So the answer is going to be C. Next slide. Okay, next slide. Use the table below to answer the question that follows, and down at the bottom, the value of delta S standard for this reaction is blank. So we want to use this column over here on the far right because we're trying to find delta S. And so what we want to do is the same thing we've done before. We want to take the products minus the reactants. Okay, and these are all, notice these are all in the gas form. You have to kind of watch this because some of these things have, for example, this right here, you've got, well, let's see, where is it? Carbon, C2H, no, I guess you don't. Okay. So, but sometimes you'll have a chart where it'll have something as a liquid, and then it'll also have it as a gas, like water, for example. All right, so C2H4 in the gas form is right here. So just come over here to the S column for that, and that's 219. So we're going to start off with that, and it's plus 219, and then it's going to be minus whatever the value is for C2H2, which is going to be this one right here, and its value is 200, approximately 201. So that's about, I guess, 18, right, when we subtract that. And then for H2, it's 130, so we're going to wind up with 18 minus 130, which is going to be about minus 112. And that's all you have to do. So I think it's going to be something like minus 112. So let's look here at the answer choices. Come across, this one is 112, but it's plus, so that one's out. This one's too high here, and here looks like our correct answer. Okay, so again, just to review this very quickly, Just use this thing down here at the bottom, which I've now obliterated with red lines, but use that thing right there and do the products times their coefficients minus the reactants times their coefficients, but these coefficients in this case are all 1. Next slide. And the answer is over here on the right-hand side. Okay, next slide. Oh, and I guess that's it. Okay, so if you want to do some more practice, which if you have time, it would be a good idea, go to Mr. Mack's website. And actually, I meant to say this at the beginning of the show here, but this is another source that I've used for these problems. It's called Mr. Mack's AP Chemistry website, where Mr. Mack is an individual in Canada who teaches, I believe, in high school, and he teaches AP Chemistry, which is the equivalent, supposedly, and it very possibly is, of first-year chemistry in college. So here's the actual website, or if you want, you can just go to Google or DuckDuckGo and type in Mr. Mack's AP Chemistry website. And he's got every chapter, basically. In 1412, he may not have every chapter, I'm not sure, and I'm going from memory, but I think there's a chapter at the end, like maybe the nuclear chemistry, or maybe the organic chemistry that he doesn't do, but he's got the rest of them. Next slide. All right, so this was only 41 minutes, so that's good because it means the file size is smaller, so it won't take so long. So I will see you in chapter 20.